Okay, so welcome back. We'll introduce the first speaker of this session. So we are happy to welcome Eliana Amazo-Gomez, and she will talk about probing the stellar magnetism of young Sun Iota-Horologii from the photosphere of its corona. You have 12 minutes, and then we have 3 minutes for questions.
Thank you so much. I would like to thank first the organizers, also the attendants here, for giving me the time to present part of the work we are doing at the Leibniz Institute in Potsdam. And this work is also published. Part of the work I am presenting today is published in this paper. Then if 12 minutes is not enough for presenting everything, then you can go and give an eye on it. But let me start from the beginning. And why Iota-Horologii is one of the most important stars in our study, and why characterizing stars that are dominated by facula or spots is important to understand the magnetic field behavior on sun-like stars. Then, in here, I am presenting you 4 different realizations of light curves model with different time life of spots, where you can see that while the input in the simulations are 30 days rotation period, this is the power spectra of the light curve, you will find that for spots that decay faster than the rotation, you lose the signal. And here we have the power spectra in a linear scale, and you also don't have a clear signal of the rotation. But then we went to the gradient of the power spectra and saw that there is an enhanced signal. Actually, there are 2 enhanced signals that are very stable, that are also proportional to the rotation period and have some amplitude that can be detected very easily. This is the case of spots. But when we compare with facula, we see that for singular cases, we were able to recover the rotation period in the light curves. But in real stars as the sun, we don't have only spots or only facula. We have the superposition of both effects. And when we have the superposition of both, what we can see is that the rotation signal is completely wrong in the power spectrum. While if we go to the gradient of the power spectra, we still see the enhanced peaks in the higher frequencies and lower frequencies. But now, more important, are not just proportional to the rotation period, but we can discriminate whether we have spot-dominated light curves or facula-dominated light curves. Also, the relative amplitude difference between these 2 peaks will allow us to discriminate whether we have more facula or spots in our light curves. And here I am presenting you 3 different cases of spot-dominated variability, solar case in the middle, and facula-dominated case, where we observe the stability of the inflection point detected in the gradient of the power spectra over time. And what we see is that this shift we observe, and I presented before, is there. And for the facular case, we also observe a secondary peak that is very stable. We went and checked if it was something related with the rotation period, and then we calculate not just for one single rotation, but for many cases of rotations. And we plot the alpha factor in this case in terms of facula to spot ratio in the simulations. The alpha factor is just the location of this inflection point over the rotation period in the simulation. And what we observe is this differentiation between the spot-dominated regime and facula-dominated regime. We wanted to know if this was just based on models. Viewing models can do many things, but you have to go and ask to the observations. And the first object is the sun to go and ask, and we observe more than 20 years of total solar irradiance. And we follow also with the MDI cameras whether we have facula and spots and characterize where is located the sun in this diagram. And we observe that the sun is in the transition region between these two domains. But well, the sun is just a single star. We have to go and check more statistics. Then we observe around 400 stars from the Kepler field. And what we observe is that this field is dominated by spot-dominated stars. And there is a lack on sun-like stars. We expect that with Plato observations, we can fill this gap, but we confirm what we observe in the models. Okay, but photometry is just one ingredient. It gives you some information, but not all. And we wanted also to know if a spectroscopy could tell us something about the activity of the star. Then we check the indicators of activity. In this case, I'm showing you S-index in terms of our alpha factor. And we recover the trend we observe in the models as well. We also check another indicators here. We also have, well, our S-index, where we observe that spot-dominated stars tend to have higher activity, while facula-dominated stars less activity. We also check H-alpha, the magnetic field, but the longitudinal magnetic field is an integrated value that also cancel each other. It depends on the sign of the magnetic field. Then we wanted to check not just the longitudinal magnetic field, but the complexity of the magnetic field of some of those stars. In here we have infamous confusiogram, maybe some of you know it, where we have the mass of the star in terms of the rotation period, and the shape of the symbol just tell us about the complexity. The shape tell us about the symmetry of the field, the color about the poloidality of the field, and the size about the magnitude of the field. We took then some of the solar-like stars and followed them by phase, recovering the magnetic map of them, and check how is the complexity of these objects. And then is when Iota-Horologii enters. Iota-Horologii is one of the stars that is starting the transition region toward facula-dominated star, but it's still a spot-dominated star. And it's a very important star that we follow for more than 20 years in calcium. But also in this diagram of von Vitense, we have that the star is located in the base of the cycle rotation period, where we have a non-active and an active branch. And it's very important to understand the base of this diagram. We also see that Iota-Horologii is a very close analog of the sun. It's around 600 megayears and have a very short coronal cycle that we follow for around 6 years. And we have also the comparison in calcium for the star, the chromosphere, and we found this beating period of the star. We follow the star also, well, with the following of polarimetry, we were able to retrieve 18 Zeeman Doppler imaging maps to characterize the cycle of the star, but also a simultaneous HST time in one of the periods of HARPS observations. Unfortunately, when we went observing the star for this period, exactly the night of observations with HST, the clouds appear in La Silla, and we could not observe the polarimetry, but at least we have the day before that it was a good proxy to compare different parameters of the activity of the star. And it will tell us many things about the stratospheric behavior of a spot-dominated star. We also were able to retrieve the map of the season. This is a magnetic map approximation of the star. And we also analyzed different lines giving us analysis of the photosphere, the chromosphere, the transition region, and in the corona too. We wanted to also constrain the astrosphere of the star with a Lyman alpha, but unfortunately, all the line was extinguished due to the Coulomb density we have in the line of sight of the star. But in the third visit of the instrument of HST, we were lucky and we observe an enhancement in the flux that is characteristic of a flare. Then we got a flare in this passing, in this visit of the star, telling us that there is an outflow in the chromosphere of the star, in the transition region. Then Iota-Horologii becomes one of the first star based in this part of the diagram of the spot-dominated, facula-dominated diagram that we are analyzing. We have plenty of data. We will retrieve more information in upcoming papers, but the idea is that we also will observe more stars. We already got XMM time for following 5 more objects, and we are asking for more time in the next proposal for the next year in XMM Newton. The idea is to understand from where comes from the difference, the magnetic difference of having a spot-dominated star and a facula-dominated star. What we believe with what we have now is that the difference is the magnetic field structure and the stability of the magnetic flux emergency in the photosphere of those stars that tend to prevail spots for more active and more stable fields, and facula for more for less simple, less complex and more simple magnetic configurations in the facula-dominated case. And with that, I want just to give you to take messages, but the most important is, if you are part of a TAC committee, please give time to these slow rotators that needs polarimetry. And I understand that follow a star for more than 20 years with 20 days with an instrument that is very expensive, is hard, but we need to understand the physics of those objects that are like the sun. Thank you so much.
Okay, thank you very much for this very nice talk. Are there questions? Are you asking a question? Or... Oh. We have time for maybe 1 or 2 questions. So over here.
So you show the plot of the cycle of the star as a function of rotation period. Did you find any correlation of that with the facula and spot regime? Like, are those 2 regimes correlated at all?
This plot, you mean?
Yeah, the one on the right.
Well, what we think is that the rotation period of the star that is located around 7 days gave us, well, the first approximation to a singular period, but in this case, we got a beating period. We have a double cycle that is not easy to understand. We are now running some dynamo simulations to understand why we obtain this double cycle. Is very fast, fortunately. And then part of the analysis we are trying to do is connect how this double cycle, this double beating pattern, will also lead us to generation of a cycle from the dynamo models. And it's a working process we are doing also with Gustavo Guerrero to understand why this beating pattern we have, while in the sun we have this clear correlation of 11 years activity cycle with our rotation period that is over there. And, it's something that we still have to dig a bit more, but we are doing now dynamo simulations for understanding that.
Okay, thank you very much. We can have 1 short question. Okay, over here, very quick.
In thinking about the beating cycle, have you ruled out any binarity or unseen companions in the system?
It's actually a very good question. It's the only single star we have that have this kind of follow-up in X-rays and in calcium. Some other stars like, I don't remember well. There are 5 stars that have some follow-up in X-rays. Those other 4 stars are binaries. This is the only single star we have. But
Thank
have
you.
a Jupiter planet at 1 astronomical unit. Then it's also important to understand the environment that this planet is involved to.
Great, thank you. So let's thank Eliana again. Okay, so we welcome the next speaker of the session, Julio Chanamé, and he will talk about does the helium-flash add to the lithium budget of the universe? So, okay, we're here already. Good.
This one. Okay. Okay, hello, good morning, everyone. I am Julio Chanamé. I work at Universidad Católica in Chile. I want to thank the organizers also for letting me talk about this subject that has been capturing my attention the last few years. So there is a clear posed question here. Does the helium flash, okay, produces lithium or not? And that's what we're trying to answer. So this is going to involve talking about the red giant branch and lithium-rich giants in general. So this is the focus of this talk. I am going to give an overview of what we have learned in the last few years about these lithium-rich giants in particular, and thanks to asteroseismology especially. So let's get there just to remind ourselves what are the lithium production channels that we know of. So it has been produced in the Big Bang, one of the few elements, right, in cosmological times. So this is why astronomers use or observe, right, lithium in very low mass star, very low metallicity, very old stars in order to understand the early universe. There are problems there, but these don't relate to this talk, okay? So a little bit of lithium was created there. Then we knew that asymptotic giant branch stars also produces lithium, okay? So there is this hot bottom burning being produced at the top of the hydrogen burning shell in these kind of stars, and then convection is able, with that structure, to bring it up, okay? And we observe that during these thermal pulses of AGVs. Thermal pulses are actually little helium flashes, which is something interesting to realize. So there's that. There's novae. This is a recent result as well. People understood recently that novae actually are the main producers of lithium in the galaxy. Like 70 to 80% of the lithium we observe actually comes from those objects. So, and then a little bit, it's a strange looking phenomenon. So it's the spallation of dust particles by cosmic rays in the interstellar medium. Also produces lithium, but very, very small quantities of it. So just for completeness. And then this, you look at this list and it's very fundamental, okay? So adding anything new there should, require, it's important and should require strong evidence, okay? And recently, people have been advocating for the helium flash of low mass stars, adding to this budget of lithium in the universe. And this is what I'm going to talk about. So what happens to lithium in low mass stars in the post-main sequence? So we have this keep in hand diagram. So we see the main sequence here, right? At the top of a star, of a low mass star, there's a cool region, so lithium survives. In the interior, it's too hot for it to survive. Very simple looking, but we don't understand it anyway. Okay, this is the simple, right? The simple picture, which doesn't work really. But we are not going to talk about main sequence here. We go to the post main sequence, and in the post main sequence, what we know pretty much, and I think it's very sound knowledge. We have that this outer convective envelope deepens a lot in mass, okay, and brings all the lithium that was in the surfaces down, and not only this can destroy it, I mean, not only dilutes it because it's mixing it with more and more and more and more mass, so it dilutes the lithium, but also can burn it because it brings it down to hotter and hotter regions, okay? And this is in the standard model of stellar evolution of low mass stars, the only event that destroys lithium, okay? But even with that single event, we predict that the abundance of lithium in this scale, A, okay, shouldn't be larger than this 1.5x, more or less. And this is why people finding things, giants, with more than that abundance, okay, claim that those are lithium rich, okay? So let's move on and look at actual data. Okay, this is a global cluster, an interesting object because we actually see the evolutionary phases, right? And you see there the main sequence, okay, which is called the spike plateau, okay? That difference between the spike plateau and the W map gray band here is the cosmological lithium problem. And then after the main sequence, you can see it here, right? There is a drop in the abundance of lithium. And that is our first dredge-up, very standard. Okay, so great. After that dredge-up, we have this plateau. So the upper red giant branch, or actually the stars started to climb the red giant branch. And again, as I mentioned earlier, there's no more mixing events in the standard evolution, but you can see that there's something else. Okay, and that thing happens at the luminosity function bump, or the RGB bump. Okay, and the RGB bump, it happens right here when the hydrogen burning shell crosses this discontinuity left by the convective envelope. Okay, something happens there. We know that now because there is this decrease in abundances, not only in lithium, but in all other light elements we see it. Okay, so this is the so-called non-standard extra mixing, thermohaline mixing, whatever mixing. We don't know what mixing, but we know it happens. Okay, so there are candidates, of course, but we don't know which exactly because the physics are still missing. And the very important point that I also want you to take to get away with is that we know that this happens to all low mass stars now. It is ubiquitous to all low mass stars. Okay, very important. Okay, let's go on. The message again is lithium is largely destroyed, okay, on the RGB. In all these models, there's no creation events, okay? And then I'm going to get to this plot. This is going to be the main plot of what follows in my talk, okay? It's lithium now in the x-axis and luminosity in the vertical axis. Okay, this is a paper that appeared a few years ago, and it used Gala data. This plot is the same as the one I was showing before, only that rotated. Okay, same thing. So this is Gala data. So now we are not in a gloral cluster, but in the field, many more stars. Okay, hundreds of thousands of stars, and with very good luminosities thanks to Gaia. Okay, and this is the behavior, and you can see the main sequence here: the turn off, first dredge up, then up to this luminosity function bump, and then the extra mixing thing until the tip of the RGB. And after the tip of the RGB, you have your clamp, right? Your horizontal branch, and that's it, basically. So that's the data. Thanks. And this is what we are going to discuss now, okay? And there are two locations that we are going to focus on. So there are the regular clamp or horizontal branch, okay? And then these things on the left at high lithium, you see here is the 1.5 line. All these are the classical lithium-rich giants. 40-year-old problem in stellar evolution without solution yet, okay? So we can focus on those first, and then we are going to go for the regular clamp, let's say. So I'm going to put that figure here so that we don't forget about it, and I'm going to show you this plot. It's very recent from this year, okay? And it's the same axis, lithium here, log L here, and there is much less data, okay? But it is equally or more important than this one. Why? Because these are asteroseismic masses, okay, from the Kepler field, particularly, and the lithium abundances are from LAMOST. Here, the masses are not that clear, okay, because they are based on luminosity and, effective temperature, etc. These are more fundamental from astroseismology. And you can see here that the authors have colored their data in two colors, red and black. And these P and S, they mean primary red clamp and secondary red clamp. And if you look at the data, there is a stark difference. After lithium of 2, to the left, there are only red points, okay? And what is primary and secondary? Mass. That's the most fundamental property of a star, right? So the primary red clamp are things with less than 2 solar masses, and the secondary with more than 2 solar masses, more massive than that. And this is evidence, in my opinion at least, for the helium-flash having something to do about this, okay? Because we learned, right, that 2 solar masses is the limit, more or less, below which you have a degenerate core, so that your helium ignition is explosive and you have a flash, okay? And above that is not explosive and you don't have a flash, okay? And you see that all the lithium-rich giants here are below 2 solar masses. So that's evidence, it's not proof. It doesn't tell me how, it is just evidence, okay, indirect if you want. Let's move on. This is a plot of one of my students, Almendra del Moral in Chile, It's the same plot, lithium on the x-axis, luminosity here, but with more statistics. And she changed the colors here, sorry. But the primary ones are the smaller, less massive than 2, are the blue points, and you can see it's the same result, only blue points to the left of the lithium-rich limit, okay? But with more statistics, she went beyond. What did she do? She looked at their metallicity. Because something else about the lithium-flash, the helium-flash, sorry, is that it is metallicity dependent. A star with less metallicity, less metallic, is hotter, and therefore can reach the ignition point of helium, for example, okay, at smaller masses. Okay, and this is what you see here from an old work by Leo Girardi. You can see the masses of the top mass of the helium flash as a function of metallicity goes up with metallicity. So she looked at that. She did 2 beams of metallicity. Hopefully you can see them here. On the left are metal poor stars. On the right, metal rich stars. And this line here is the most massive one on the left. So you can see that in the metal rich regime, there are more massive stars, as the helium flash predicts. So again, more evidence now that the helium flash is involved, but the problem or the question is it ubiquitous? And this is the key here, okay? Because these lithium rich giants are only a small fraction of the population. So now in order to answer the ubiquitous question, we have to go to the normal clamp, okay? And this is what I did, and I'm going to go a little bit fast here. So I'm going to explain the problem. In this figure here, you can see also a line. This line is a 1 solar mass model at solar metallicity, and it really tracks the behavior of the data, okay? Except at the clamp, because the predicted clamp is here, and the actual clamp is here. And there is a factor of 40 difference there, which led these people, to write in Nature that it is ubiquitous. The problem, what is the problem here? The problem is that this is not a global cluster with 1 solar mass giants, but this is the field, right? In the field, you have a distribution. I'm going there. You have a distribution, and you have to account for that. And the result is this. Sorry, this one. Okay, your low mass stars are really, really lithium poor, but the more massive ones are actually populating the clamp. Okay, so it is not ubiquitous. Okay, mass matters. And these are my conclusions, and thank you for your attention.
Well, thank you very much. We only have time for one short question, so please go ahead. There's one over there.
Very interesting talk. I just wanted to ask, there is a scenario, the merger scenario to explain the super lithium rich stars. And recently, for example, the merger of helium white dwarf and red giant. And I just wanted to ask, what do you think of that?
That's one I haven't looked at, sorry. So there is, I mean, there's a simpler one, which involves binaries, closed binaries. And maybe it's related to the merger eventually, right? But so the specific one of about 2 stars merging, I haven't looked at it, sorry. The closed binaries, it is still in the air, but I mean, there is one clear prediction of that scenario, the closed binaries being, the scenario works like this. You have a closed binary and you have your giant, and the closed binary induces tides, right, on the other star. And those tides induce this mixing in the interior that is needed. So a clear prediction of that is that all red lithium-rich giants should have close companions. We are looking into that, and it doesn't seem to be the case. It's similar to the fraction of other stars with no lithium-rich atmospheres. So I don't know, but sorry, I didn't look into this other one. Thank you.
Okay, thank you very much. So let's thank Julio again. And our next speaker is Keiichi Ohnaka, and he will talk about ALMA imaging of the complex dynamical atmosphere of the AGB star W Hya at 20 milliarc-second resolution. There we go.
All right. Okay, yeah. First of all, I would like to thank SOC for giving me an opportunity to talk about our recent results on high resolution imaging of this AGB star W Hya. And here is my collaborator, cut that one at the Uppsala University in Sweden. So first of all, a very quick introduction about mass loss at the asymptotic giant branch phase. So stars at the AGB phase start to lose mass at a significant mass loss rate up to 10 to the minus 4 solar mass per year. And the problem is the mechanism behind this mass loss is a long-standing problem, and it is often attributed to the radiation pressure on dust grains, as illustrated here. So the idea is, in these cool stars, dust grains can form, do form, and then those dust grains absorb or scatter stellar photons. So the momentum is transferred from stellar photons to the dust grains, pushing the grains outward and dragging the gas together. So this is the idea. However, oops, sorry. Maybe it's better this way. However, it is not clear how dust forms from the molecular gas. Also, mass loss is seen in stars with little or no dust. So maybe there are other mechanisms in operation, for example, MHD process or radiation pressure on molecules or something else. So this is the idea or the scientific driver behind our research. Now, we talk about our target W Hya, which is the third closest AGB star to the sun at a distance of 98 parsecs. And this is the light curve of W Hya taken from the AAVSO database, and it shows a clear mirror-like variation with a period of about 1 year. And what's important about W Hya is its angular diameter is 40 to 50 milliarcseconds. So 40 to 50 milliarcseconds may sound very small to you, but then actually the W Hya is one of the stars with the largest angular diameters in the sky. So this gives us opportunity to spatially resolve the star, its surface, and its circumstellar environment, which is why we observe W Hya with ALMA in band 6 from 250 to 270 gigahertz with a maximum baseline of 16 kilometers, which gave us a resolution of 16 times 20 milliarcseconds. And this is the continuum image that we got at 250 gigahertz, and the black circle shows the fit to the continuum image with a diameter of 60 milliarcseconds. And the white ellipse here, this is the beam size. So the resolution is about 3 times better or smaller or finer than the stellar surface. In other words, we can really see or resolve the stellar surface. And our observation took place in June 2019 when the star was at minimum light. And in the end, we identified nearly 60 molecular lines, different isotopologues of SiO, water vapor, and the many lines of sulfur dioxide and its isotopolog, and some lines of ALO, ALOH, TiO, HCN, and SO. So I don't have time to present all these lines. I'll be focusing on SiO and water and a little bit of sulfur dioxide. So this is the channel. This slide shows the channel maps of 30 SiO line. So from minus 10 kilometers per second, 0 and 10 kilometers per second with respect to the systemic velocity or the star's velocity. This means this image shows the material moving toward us at 10 kilometers per second. And this is the image of the material moving with the same velocity as the star, mostly in the plane of the sky. And this is the image of the material moving away from us at 10 kilometers per second. And this black circle, maybe you might see it, the black circle shows the continuum size, 60 milliarcseconds. And these are continuum subtractive maps. This means, and then within this stellar disk, well, it looks dark blue, which means negative intensity because we see absorption. So the intensity is lower than the continuum. That's why we see in the continuum subtracted maps, we see negative intensity, which means absorption. And outside the stellar disk, you can see very complicated emission. There is a plume going to the north. And here in this panel, you can see a tail going to the south. And then the extended atmosphere, elongated atmosphere approximately in east-west direction, which is asymmetric too. But all in all, we see absorption over the stellar disk, which is expected from Kirchhoff's law, because we have the continuum layer, and then there is a cool atmosphere, and you are observing the star like from there. And then you have the hot material and then cool material. So you see the absorption in front of the star as you learn in the astrophysics textbook. Good, so nice. Let's go to another 30 SIO line, the same channel map from -10 to 0 to 10 kilometers per second. And you can see again some emission, non-inhomogeneous emission. But then inside the disk, in front of the star, you see dark blue. So this means absorption is fine, but around here, something happens. Here, for example, the emission starts to go inside the stellar disk. And then we continue like this. So at these redshifted velocities, you can see the emission over the stellar disk. And then remember, these are continuum subtracted maps. So this means we see emission in front of the star instead of absorption. This is unexpected. Now we go to another SIO line, SI17O, and you can recognize the very complicated emission, very clumpy. For example, a very bright spot in the north, and then a very tail going to the south, fine. And now inside the disk, we see, well, it looks dark blue because it is absorption. That's fine. But again, around this redshifted velocity, we start to see the emission over the stellar disk instead of absorption. Now, this is clearer, even clearer for this vibrationally excited water line. Again, the same channel maps. Oops, here. Already at this velocity, we start to see emission over the stellar disk. And then it gets stronger and stronger. And at these velocities, redshift velocities, emission covers almost the entire stellar disk. Emission, not absorption. Okay. One of the SO2 lines, okay, you can see very complicated, very interesting emission. And they say, or just, I guess I forgot to mention, the field of view is 200 milliarc second or 250 by 250 milliarc seconds. So the stellar disk is 60 milliarc second, and the angular resolution is about 20 milliarc seconds. So we are really looking at details over the stellar disk and the atmosphere within a few stellar radii. And then we see a number of interesting features, but here we already see emission over the stellar disk. And here at this panel, you can see a very bright spot inside or in front of the star, not absorption. Now, let's go to another SO2 line. But here, okay, we see many features, that's fine. But then over the stellar disk, well, it looks dark blue because we see absorption, no emission. So the same SO2 lines, but one line shows emission, one line only absorption, as expected. So far the summary is we see everywhere irregular shaped clumpy emission, plume, tail, and so on. But the point is, some lines show emission over the stellar disk, some lines no. And this redshifted emission over the stellar disk is particularly strong in this vibrationally excited water line, and this strongly suggests maser activities. So now let's consider conditions for maser for this water transition. Baudry et al. Recently showed that we need high water density and rather high dust temperature, nearly close to dust condensation temperature, and the kinetic temperature below 1000 K. So in other words, these measures trace cool and dense regions or pockets, and these pockets might be a consequence of convection. So what's shown here is a snapshot of 3D convection model by Höfner and Freitag. So this is the intensity model, and model intensity, and then this is the density map, which shows the significant irregularities. So maybe the water may resonate in those the cool, dense convective cells. But the question is, the cool, dense environment is exactly favorable for dust formation. So a legitimate question is, dust forms as well? We check that by taking a look at the polarized intensity map, because polarized intensity shows us the dust cloud distribution. And fortunately, not just 9 days before our ALMA observation, there was a VLT sphere simple observation with a 20 milliarcsecond resolution comparable to our ALMA data. And then we overlap. So this is the integrated intensity map of water masers. And this is the polarized intensity map taken at 820 nanometers indivisible. And then if we compare, so now the contours are the water masers. We can see a good overlap. For example, here we see the dust formation and masers in the west, and then there is a thing sticking out to the north. We see good agreement. So the answer is yes, both water masers and dust are tracing cool and dense pockets, probably a consequence of convection. So, okay, I skipped this slide. And now what to do now? We need a quantitative modeling to derive density, temperature, and velocity field. And the last but not the least, we are also working on the VLTI 4-micron interferometric imaging. And this is what I want to show in the last. So again, these VLTI data were taken contemporaneously with ALMA data within 10 days or so. Then these the ALMA images, different molecular lines, and this is the very preliminary image reconstructed from VLTI Matisse data at 4 micron, and you can see a very tiny speck here. This is the beam size of 6 milliarcseconds. So we can probe the region, the detail of the region inside the region that we probe with ALMA. So the conclusion is, with multi-wavelength high-resolution imaging, we can not only resolve the stellar atmosphere and take nice images, but also our goal is to resolve the mass loss mechanism in AGB stars. Okay, I stop here and thank you for your attention.
Okay, thank you very much. We have time for one short question, one quick urgent question. There's one over there.
Hello, thank you very much for your talk. It's very nice that you combine interferometric observation with ALMA and Matisse. My question is, would you be interested in probing the environment of the star using gravity in the K-band? Oh.
I guess gravity, the VLTI instrument.
Yes.
Yes. So two. Yes, basically yes, but I myself don't have gravity data, but then there was an instrument working in the K-band 2 micron region, called AMBER before gravity, with even higher spectral resolution. So yes, but then not contemporaneous. So then for this data set, the Matisse, sphere simple, and ALMA, they are the contemporaneous data. Yes, but then there will be a different epoch.
Okay, great. So let's thank Keiichi again. And welcome our next speakers. Our next speaker is Missael Hernández Huerta. Okay. Can we get the other mic? Yeah.
Gracias.
Right. and he will talk about the impact of evolutionary status on cool giant stellar activity levels.
Bueno, hola a todos. En efecto, yo les voy a estar hablando un poquito sobre este proyecto, que como bien dice su nombre, pues va más que nada sobre actividad. Entonces, pues la primera pregunta que es natural plantearse o que es importante responder sería, pues, exacto, ¿no? ¿Por qué es importante estudiar la actividad en primer lugar? O sea, obviamente habrá muchas razones, pero a mí me gusta destacar estas tres. Entonces, la primera es, obviamente, que nos ayuda a comprender mejor la física estelar. También los fenómenos de actividad conducen todo lo que es el clima espacial, de modo que tiene un impacto directo sobre los exoplanetas y sobre su potencial habitabilidad, así que bueno, también es importante en ese sentido. Y por supuesto nos ayuda a entender mejor a nuestro propio Sol, porque la idea es poder entender al Sol dentro de su propio contexto estelar. Ahora bien, ya hablando de la actividad, bueno, en este trabajo utilizamos el índice S, que es un índice muy popular, muy utilizado, y cuyos orígenes se remontan a hace más de 100 años, cuando Everard y Schwarzschild notaron en el espectro de Arturo que los núcleos de absorción de las líneas de resonancia H y K de calcio 2 mostraban una prominente emisión justo ahí en el centro. ¿Qué es lo que ocurre? Esta emisión. ¿Qué es lo que ocurre en las zonas magnéticamente perturbadas, es decir, activas del Sol? Y se debe a la diferencia de temperaturas entre la fotosfera y la cromósfera calentada por la actividad. Entonces, luego en la década de los 60, en el Mount Wilson, se inició un proyecto de monitoreo y se introdujo el índice S, que simplemente es esta división, ¿no? O sea, es el flujo medido en los núcleos de absorción de las líneas H de calcio 2, simplemente pesado en el pseudocontinuo de la estrella, medido en dos filtros más amplios. Ya hablando un poco más sobre qué es lo que ocurre con la evolución, bueno, con la evolución de la actividad conforme las estrellas envejecen, resulta que tenemos mucha evidencia agrupada básicamente en dos frentes, que si bien no es que sean opuestos, sí que apuntan en direcciones algo distintas. Por un lado, tenemos un montón de resultados que nos indican que dentro de la secuencia principal y justo después de ella, las estrellas deberían estar perdiendo monotónicamente su actividad. Es decir, mientras evolucionan dentro de la secuencia principal, se ha mostrado y se ha observado que la actividad se va perdiendo, además de que estrellas que acaban de salir de la secuencia principal se encuentran en mínimos de actividad, e incluso si uno se va a la zona de las gigantes más frías, resulta que en rayos X uno puede ver que los gigantes más fríos ni siquiera tienen coronas. Entonces, todo eso apunta a que las estrellas deberían estar perdiendo actividad constantemente. Pero, por otro lado, tenemos otro grupo de resultados que nos indican que, bueno, esto puede que no sea así de simple, porque se encuentran señales de actividad por todos lados en el diagrama HR, y se ha propuesto que estas disparidades en el comportamiento de la actividad en la zona de las gigantes podría ser atribuido a que son muy dispares en evolución, porque lo son en masa. Este resultado de aquí es también muy importante porque es el que puso sobre la mesa la idea de que conforme las estrellas se hinchan, es decir, se hacen gigantes, pues en realidad su núcleo se está contrayendo y eso provoca que se acelere, de modo que el momento angular dentro de la estrella se redistribuye y perfectamente podría haber una reactivación del dínamo interno, y es decir, de la actividad. Entonces resulta evidente que es interesante ver qué es lo que está pasando justo en el medio. O sea, al salir de la secuencia principal y al migrar hacia la zona de las gigantes, bueno, tenemos esta etapa intermedia del quemado central de helio, que necesitamos que ocurra de manera más o menos estable, no explosiva, como en el flash de helio. Y es interesante entonces ver con lujo de detalle qué es lo que está pasando ahí en el medio con la actividad. Y en ese sentido, este artículo del 2020, ¿qué acabo de hacer? Es el punto de partida perfecto, es el que marcó la pauta que queremos seguir. O sea, porque en este artículo se encontró, bueno, se utilizaron los 4 gigantes tipo K de las Híades y se mostró que se agrupan en pares. El primer par es bastante más activo, pero es menos evolucionado porque es menos masivo. Y el segundo par es un poco más masivo, más evolucionado y menos activo. Entonces, el punto es poder recolectar más observaciones y monitorear la actividad en esta región particular de la evolución y del diagrama. Así que lo que hicimos fue hacernos nuestra propia muestra de estrellas. Utilizamos 24 estrellas, digamos, de campo, estrellas frías, pero incluimos también cuatro gigantes tipo K del mismo cúmulo estelar, que en este caso es M41, de modo que podemos asumir que son de la misma edad, y eso es una restricción importante a la hora de modelar su etapa evolutiva y su masa. Entonces hicimos algunas observaciones, calculamos la luminosidad con un poquito de fotometría, utilizamos paralajes recientes del Data Release 3 de Gaia para obtener la luminosidad, y la temperatura efectiva simplemente la obtuvimos con un modelado espectral de nuestras observaciones hechas con el Tigre, que es nuestro propio telescopio robótico que se encuentra en Guanajuato, en México. Y de ese modo podemos construirnos nuestro diagrama para todas las estrellas y ponernos a comparar con trayectorias de evolución, que en nuestro caso utilizamos el código de Eggleton, que está muy bien calibrado con el overshooting, que es especialmente importante para las luminosidades del Blue Loop, que es donde queremos estar observando las estrellas. Pero ahora bien, un problema común a la hora de utilizar trayectorias de evolución es que un mismo punto en el diagrama HR puede ser reproducido por más de una trayectoria, o incluso una sola trayectoria puede doblarse sobre sí misma y pasar varias veces por el mismo punto. Así que lo que hicimos fue darle preferencia a las etapas más lentamente vividas, es decir, aquellas que son más probables de observar. En el caso de las 4 estrellas de M41, podemos utilizar la restricción de la edad y asumir entonces que las trayectorias que reproduzcan las posiciones de estas 4 estrellas deben, si bien no solo empatar bien la masa, deben ser de la misma edad. Y eso es una restricción muy útil. En este caso encontramos 2 soluciones que cumplen esas características, así que para decidir entre una y otra, bueno, estas son las dos soluciones, digamos, que es importante decidir entre una y otra porque son esencialmente distintas. Por ejemplo, esta estrella de aquí, en una de las soluciones, está saliendo de su Blue Loop, es decir, a la salida de su quemado central de helio, mientras que en la otra solución está al inicio de ella. Entonces es importante distinguir entre estos 2 escenarios. Para hacerlo, bueno, podemos asumir que la probabilidad de encontrar a una estrella en una cierta posición de una cierta trayectoria válida, pues es simplemente el tamaño temporal de su posición dividido entre la duración total de esa trayectoria. Y en nuestro caso, que tenemos soluciones que constan de 4 estrellas, pues la probabilidad total de una de esas soluciones será simplemente el producto de las 4 probabilidades individuales. Para computar esas, bueno, pues ahí tenemos los modelos. Entonces podemos utilizar densidad de marcas de edad equidistantes en el tiempo, como esta de aquí. Esta es una estrellita, y podemos saber cuál es el tamaño de su posición utilizando las marcas de edad. Este es un ejemplo de cómo se obtuvo este tiempo, que sería de 0.02 millones de años. Y aquí hay otro ejemplo de otra estrella que está pasando justamente por el Blue Loop, es decir, una etapa más estable, y su tamaño será un poco superior. Pero el punto es que podemos repetir eso para todas las estrellas y calcular este cociente. Aquí lo único importante es que se puede obtener que en realidad una de las soluciones es al menos del orden de 10.000 veces más probable que la otra, entonces es la que adoptaremos como válida, que en este caso era la primera que les mostré. Esto debería ser un GIF, que desafortunadamente no podemos reproducir, pero es una animación muy bonita de cómo las diferentes trayectorias de diferentes masas van empatando con la misma marca de edad todas las posiciones, ¿no? Que sería la recreación de una isócrona, pero se la van a tener que imaginar. Y bueno, ahora ya viendo qué es lo que ocurría, en particular con las mediciones del índice S, pues tenemos este tipo de comportamiento. Tenemos a todos nuestros gigantes ahí bien agrupaditos en la zona de los gigantes, exhibiendo diferentes niveles de actividad, muy heterogéneos, pero bueno, todo eso puede ser entendido en el contexto de la evolución, porque todas ellas serán estrellas en diferentes etapas de evolución. Entonces, esta disparidad en actividad se explica por esa disparidad en evolución. Lo interesante es que si uno las agrupa digamos, en categorías un poco más amplias, pero válidas, pues sí que se muestra un comportamiento interesante, ¿no? O sea, tenemos a las crossers, que son aquellas estrellas que acaban de salir de la secuencia principal y están cruzando el Hertzsprung Gap. Y al llegar a la RGB, resulta que sí parece haber una reactivación de actividad. Mientras que aquellas que ya están en la AGB, pues sí que son las más inactivas de todas. Entonces, el punto es que en efecto algo está ocurriendo en esa etapa intermedia, que es estable, entonces hay suficiente tiempo para explorarla con lujo de detalle evolutivo. Y también tenemos que los gigantes más fríos, aquellos que ni siquiera tienen corona, de acuerdo con la línea divisoria de Linsky-Heish, pues sí, sistemáticamente muestran un índice S menor, de modo que estamos reproduciendo el mismo comportamiento, a pesar de que estamos solo realizando observaciones en el ultravioleta, y esta línea pues es solo sensible a los rayos X. Pero bueno, ahí se confirma algo también muy interesante. Y bueno, estas 4 estrellas aquí encerradas son justamente los 4 gigantes del cúmulo de M41 que están pasando por el Blue Loop, demostrando, o bueno, haciéndonos notar que justamente esta etapa es bastante crucial para explorar, porque es donde ocurren los cambios interesantes. Y la idea es poder seguir explorando esta edad, ¿no? Porque idealmente queremos mapear con suficiente lujo de detalle evolutivo qué es exactamente lo que está pasando en cada etapa relativa de avance dentro del Blue Loop, con más cúmulos estelares que permiten modelar, digamos, muy precisamente la edad de todas las estrellas. Así que hay un poco de trabajo futuro. Y eso sería todo.
Thank you very much. So we have time for questions. Does anybody have a question? Or a comment or a suggestion? You can do it in Spanish or English. No? Okay, I think everybody's very convinced. So let's thank Missael again. Well. Okay, so coming up, let me find my. So the next speaker of this session is Natalia Oliveros-Gomez. Perdón, sorry, Natalia Oliveros-Gomez. And she will talk about systematic method for identification of L-type variable brown dwarfs.
Hola. Bueno, nos movemos de las supergigantes a las enanas marrones, que es un cambio drástico. Pero sí, me presento. Este proyecto hace parte, bueno, hizo parte de mi tesis de maestría en la Universidad de Guanajuato, que sustenté la semana pasada. Y mi asesora fue Eliana Amazo-Gomez y en colaboración con Daniela Bardales. Entonces, un poco de contexto de qué es una enana marrón. Básicamente son objetos subestelares bastante controversiales porque básicamente llegan a llenar un poco el gap entre estrellas y planetas, ya que comparten algunas características en términos, por ejemplo, con las estrellas de similar formación en nubes moleculares. Y en el caso de los planetas gigantes, pues comparten un poco la relación de cómo son sus atmósferas. En una charla de ayer se dio un poco de contexto sobre las atmósferas de las enanas marrones y es básicamente la razón por la que nos interesa entender un poco qué es lo que sucede en sus atmósferas y cómo es la estructura interna. Entonces, tenemos 3 tipos de enanas marrones, de acuerdo pues a su temperatura y a sus características espectrales. En este trabajo nos vamos a enfocar en las tipo L, que son las más calientes de las enanas. Aquí, bueno, la forma en cómo estudiamos las enanas marrones, digamos desde la parte observacional, puede ser, por ejemplo, desde la fotometría, donde tenemos 2 tipos de comportamiento. En uno de ellos, por ejemplo, vemos enanas marrones que presentan cierta variabilidad, como en este caso, en cuestión de horas, y esa variabilidad es asociada a la misma rotación de estos objetos, ya que pueden presentar nubes un poco similar en el caso, por ejemplo, de Júpiter, y esas nubes al rotar, pues nos están generando esa variación en el flujo. Sin embargo, no todos los objetos que se observan presentan variabilidad, a pesar de que, por ejemplo, este es un tipo espectral bastante similar, este objeto no presenta variabilidad. Entonces, ahí nos surge la pregunta de por qué ocurre esto, de que unos objetos sí presentan variabilidad y otros no. Y básicamente los objetos que sí muestran variabilidad vendrían siendo los más importantes de estudiar para entender un poco mejor cómo es la estructura de estos objetos. Desde la espectroscopía, también otros artículos nos muestran que no solamente hay una variación de flujo total, sino que además hay una variabilidad para diferentes longitudes de onda si comparamos en el caso de las L, esa variación es un poco más lineal, y en el caso de las T, pues los picos de estas dos bandas presentan un poco más de variabilidad. Entonces, esto nos da una idea de cómo puede ser la distribución de nubes dentro de la atmósfera para generar esa variabilidad que estamos observando. Entonces, básicamente, la única manera ahora que tenemos para estudiar o para seleccionar qué objetos son variables o no variables es pues dedicando mucho tiempo de observación a cada objeto de manera individual y pues simplemente mirar si presentan variabilidad o no. Entonces, nuestra propuesta es generar un método sistemático que nos permita preseleccionar estos candidatos variables y que son los que más nos interesan para poder entender la estructura interna de la atmósfera. Y que pues nuestro método sea utilizando un solo espectro y no pues muchos espectros fotométricos, o sea, muchos espectros durante mucho tiempo. Entonces, lo primero que hicimos fue seleccionar un objeto que conocemos como variable y estudiar en diferentes longitudes de onda cuál es su comportamiento, qué partes del espectro presentan mayor o menor variabilidad. Esto lo hicimos con datos del Hubble, específicamente 66 espectros tomados durante 8 horas y media, y aquí vemos cómo se reproduce esa variabilidad que presenta el objeto en el tiempo. Con este objeto, entonces, lo que notaron en proyectos anteriores es que si se comparaban algunos índices espectrales que comparan zonas variables y no variables del espectro, se podían detectar, por ejemplo, sistemas binarios, pero dentro de esos sistemas binarios algunos errores, o sea, se seleccionaban sistemas binarios que realmente eran estrellas, bueno, enanas marrones aisladas con variabilidad. Entonces dijimos, bueno, tal vez podemos aplicar este mismo método de los índices espectrales para detectar objetos variables dentro de una muestra. Entonces, utilizamos estos índices y lo que hicimos fue comparar todos los índices entre ellos y, bueno, visualmente vemos como la separación de dos grupos que se relacionan con los espectros más variables y menos variables en la curva de luz. Y luego los clasificamos. Entonces hicimos una clasificación de los espectros más variables y menos variables usando Machine Learning para pues, hacer un poco más cuantitativa esta clasificación de los grupos. Y seleccionamos entonces a las que llamamos áreas de variabilidad aquí. Y con esto entonces dijimos, ok, necesitamos un threshold para definir cuál es el número mínimo de áreas que necesitamos para decir que un objeto evidentemente es variable, es candidato a variable o no. Y en el caso de este método lo definimos en 9, ya que, bueno, todos los no variables caen como no variables y los variables, la mayoría caen como variables. Y básicamente ese es el método que diseñamos, pero bueno, ahora necesitamos probarlo y ver que funcione. Así que aplicamos el método aplicamos todos los índices a una muestra de 75 enanas marrones y tomadas del SPETS Catalog, y básicamente esto fue lo que obtuvimos. Tenemos un porcentaje del variability fraction, que básicamente es la cantidad de objetos de nuestra muestra como candidatos variables, y lo contrastamos con otros resultados de la literatura que sí han hecho específicamente surveys de variabilidad, es decir, observaron objeto a objeto durante al menos 5 o 6 horas y obtuvieron si son variables o no. Y digamos que con nuestro método, que es usando un solo espectro tomado una vez, pues los resultados son un poco consistentes. Digamos que el cambio del porcentaje en sí se debe pues, a la sensibilidad de los instrumentos que se usan en cada uno de los proyectos o al tipo a la banda espectral que usan para estudiar esto. Y Además, dentro de nuestra lista de 75 objetos, 23 de ellos ya han sido monitoreados en algún momento en la literatura y nada más tenemos una tasa de falsos negativos del 15%, lo cual pues, es bastante buena. Y como para ya lo más importante de todo el proyecto es que pues esto lo que queremos revisar ahora es que de pronto no solamente lo podemos aplicar a enanas marrones, sino que lo podríamos aplicar a exoplanetas que cumplan, por ejemplo, con colores similares, con temperaturas efectivas similares, y de pronto, pues ahora utilizar, ya que se tienen telescopios como el James Webb, mejores datos y demás, mirar si también se pueden aplicar a este tipo de sistemas. Además, pues ya fue comprobado con una lista bastante grande y obtuvimos 31 nuevas variables, candidatas variables para estudiar en el futuro, que de hecho nuestra idea es ver si las podemos estudiar durante un tiempo fotométricamente y analizar si nuestro método sigue funcionando o aumenta o no la tasa de falsos negativos que reportamos. Y eso sería todo.
Great. So thank you, Natalia. Are there questions or comments? Okay, we have one over there.
Muy interesante tu plática. Es una pregunta de si hicieron el ejercicio de los objetos en tu muestra que se sabe que son variables, ¿qué fracción de esos se recuperan con la técnica que muestras? Como para saber qué tan eficiente es.
Sí, de los 75, de las 75 de la muestra completa, estudiados en la literatura nada más habían 23. Y de esos 23, nada más 3, nuestro método los daba como no candidatos y eran candidatos, y realmente sí se les había medido variabilidad. O incluso había como disparidad entre algunos artículos, como en ciertas bandas sí se encontraba variabilidad y en otras no. Entonces, esos igual los consideramos como falsos negativos porque no estamos seguros. O sea, ni siquiera en la literatura con observaciones durante el tiempo, algunos están totalmente confirmados como variables. Entonces, y sí, entonces dio del 15% aproximadamente.
Gracias.
Gracias por la charla, muy interesante. No me quedó claro cuántos índices usan como input para el clasificador.
6.
6. Ok.
Exactamente. Cada uno de los índices pues tiene una relación, por ejemplo, los dos primeros de la porción de mayor variabilidad cerca a la banda J contra la menor variabilidad de esa misma banda. Lo mismo con el H. Y del que se llama Max Bar es como en todo el espectro cuál es la zona más variable y la zona menos variable. Y los otros 3 fueron índices que se usaron en estudios anteriores para determinar binariedad.
¿Hicieron un análisis de la importancia de cada uno de esos features para la clasificación? Mirando los coeficientes. Supongo que es una regresión logística o un...
Sí, bueno, los índices los calculamos...
No, pero no digo del índice, sino de la importancia que tuvo el índice para generar la predicción de la clasificación.
ok. No, bueno, no, a ver, aquí en esta parte para determinar la clasificación, lo que hicimos más importante para nosotros fue como descartar las zonas de transición entre, o sea, justo estas donde de pronto no está como demasiado claro. Y lo que hicimos fue nada más tomar aquí como entre sigma para allá, para digamos que no tener ese problema. Pero no le dimos más importancia a unos índices que a otros. En este caso, pues tomamos como todos completos. Pero podría ser interesante.
El algoritmo tal vez sí le dio más importancia a unos que a otros.
Sí, podríamos. Sí.
Después lo hablamos.
Muchas gracias.
Thank you. Okay, and let's welcome the last speaker of this session. This is Rocio Kiman, and she will talk about studying radius inflation on low mass stars using Gaia data release 3.
Thank you. Yes. Hello, everyone. My name is Rocio Kiman. I'm a postdoc at the California Institute of Technology, but I'm originally from Argentina, so feel free to ask me questions in Spanish. So I'm going to put this project in context of what I in general do, that is studying ages of low mass stars. And this particular topic is very important because, well, first, M dwarfs or low mass stars, by the way, I'm going to use these two terms interchangeably during this talk. They are the most common star in the galaxy, so they can help us understand the evolution and the composition of the galaxy. But also, and I probably don't need to say this, they are the major targets in the search for Earth-like exoplanets. So understanding the ages of the host star is key to understand the evolution and the habitability of these exoplanets. So let's put it in context. The M dwarfs with this color magnitude diagram from Gaia DR2. This is a Sloan Digital Sky Survey sample. They all have spectra. That's why they are color coded by spectral type. And they have the G minus RP color in the x-axis, in the absolute magnitude in the y-axis. So just to we all agree what I mean by M dwarf, we are talking about stars of masses between 0.1 and 0.6 solar masses, effective temperatures between 2200 and 3800 Kelvin, radius between 0.1 and 0.6 solar radius, and one of the properties which I like the most is that their main sequence lifetime is longer than the current age of the universe. So we can put it in another term, that means that every single M dwarf that has ever lived is still there. So there are a lot of them, and we can definitely use this to study how they evolve. But although this is an amazing property, it has its issues. Getting ages of M dwarfs is quite challenging. Although we do have a lot of ways to study ages of higher mass stars, such as isochron fitting, astrososmology, gyrochronology, and empirical and statistical age relationships. When we go to the M dwarfs, this doesn't work. Isochron fitting, when the M dwarf gets into the main sequence, it just sits there for a long time. So there's a lot of uncertainty when using isochrons to try to get an age. Astrososmology, we haven't found pulsations on M dwarfs yet. And gyrochronology, we don't really understand how the rotation period of an M dwarf evolves. There are some tries and we're getting close to that, but we still don't have a well made picture of the evolution of the rotation period. So we're stuck with empirical and statistical age relations. And what I mean by that is using age indicators, parameters that we can measure to estimate, that are related to age, to estimate ages. And those parameters are such as color magnitude diagram position, kinematics, magnetic activity, rotation period, just to name a few. What I normally do is just study how all of these properties evolve with time, and then use those to estimate M dwarf ages. So if you have an M dwarf that you would like to have an age for, please feel free to reach out. But that's not what I'm going to talk about today. We know that all of these properties, the evolution of these properties depends on other fundamental properties of the star, such as mass, effective temperature, metallicity, and radius. So, for example, magnetic activity evolves differently when we have a higher mass star, a higher mass M dwarf, or a lower mass M dwarf. But as well, all of these properties are affected by the age-dependent properties. So this is kind of a two-way relationship, and to be able to have a clear idea of the full evolution, the big picture evolution of an M dwarf, we need to be able to understand both. And today I'm going to talk about the radius. So there is a problem that you might have heard of for lower mass stars, that models and observations for effective temperatures and radius do not agree. So there is the temperatures that we measure are a little bit lower than what the model predicts, and the radius are a little bit larger. This problem is called the radius inflation, and for some stars, we found a radius that is around 10% larger than what the model predicts for the same measured mass. One of the main culprits for this problem is magnetic activity, and that's what I've been studying. There is a lot of tests for eclipsing binaries showing a correlation between inflation and magnetic activity, but for single stars, it's not super clear. So the conclusion here is that we need model-independent ways to measure the radius, because if we only depend on the model, as the observation shows, we might get an error. So for getting a model-independent way to measure the radius, what we did was to compile a sample of main sequence stars that have angular diameter measurements and use that to calibrate the surface brightness color relationship, taking advantage of the Gaia photometry and parallax, which are extremely precise. So this is the sample of stars with angular diameter measurements, which I cross-matched with Gaia. That was also helpful to apply a lot of quality cuts to select the best possible sample. Those quality cuts are like a Rui number of less than 1.4, which removes likely binaries, signal to noise cuts in photometry and parallax, remove non-variable stars, or select non-variable stars, sorry, and select single stars, and most importantly, stars that are closer than 100 parsecs. That is to remove as much as possible the influence of extinction on this sample. So what we want to do with this then is calculate the surface brightness color relation, and to tell you what is that more or less. So we start from the Stefan Boltzmann law that can be calibrated to what the flux that we get on Earth, where theta is the angular diameter of the star, so the angle that it's in the sky. Very quickly, we can approximate the volumetric flux with the polynomial of the color and a magnitude, which is a volumetric correction, the polynomial, and then the effective temperature also with a polynomial. And with that, we get to a relation between the color, the magnitude, and angular diameter. I know that you lose part of your audience every time that you put an equation on the slide, so I probably lost all of you, but if you want to know, so this is what I care about. There is a clear relation between angular diameter, magnitude, and color. And that's what we calibrated for the Gaia magnitudes and color. So we have that quantity over here that is calculated using the magnitude and the angular diameter that we already had, and then the color on the y-axis. And there's a clear trend between the two that we fitted for the Gaia photometry. And we can, so conclusion is color, magnitude, we can estimate an angular diameter, and then combining that with the parallax, we can estimate a radius. So this is a very cheap way of getting radius of a lot of stars, and it can get to a precision like a 4%, so it's quite useful. And we did the same calibration for different colors, the 3 colors in Gaia and the 3 magnitudes in Gaia as well, so people can choose whatever is the best way. To study then the relation to radius inflation, we needed a way to estimate the magnetic activity of all of these stars, and for that we use H-alpha measurements. H-alpha is this line over here. It's 6.563 angstroms. This is a spectra from Sloan of a very active M3. And the H-alpha is emitted at the chromosphere of the star. The magnetic field hits the chromosphere, and that emits H-alpha, so that we can measure it and get an idea of how active a star is. And in particular, for M-dwarfs, this is very useful because most of the M-dwarfs, the active M-dwarfs, have H-alpha in emission. So we use a sample, again, from Sloan Digital Sky Survey that has a spectra for all of the stars, has H-alpha measurements for all of the stars, cross-match it with Gaia. We can estimate the radius with the method that I just described, and we can estimate the mass from an absolute magnitude in K, from the absolute K magnitude. And I divided the stars here in active and inactive. The inactives are in gray, and the active ones are color-coded by fractional H-alpha luminosity. So what we can see right away is that active stars have a larger radius than the inactive stars. And if we calculate approximately how much that is. It's like a 7%, which agrees with what the literature says. And that value also gets smaller for smaller masses, which is also known at around the fully convective M dwarfs, the inflation gets up to 4%, which is too close to the uncertainties in our method. So it's not easy to measure the inflation at that mass regime. But there is a clear correlation between the two. And we can see that the active stars have actually larger radius. And now we can use the same sample to see if we can find a correlation between the inflation and the H-alpha value, because this is just okay, they are larger, but let's see if there is actually a correlation with H-alpha, and that's the next thing that we did. So we calculated an average of the inactive stars radius and compare it to each of the radius of the active stars, and that is that the y-axis is that difference divided by the radius of the inactive stars. So what we could find is that for higher mass stars, this is been between 0.5 and 0.6 solar radius. We see an increase in the inflation with ranges that agree with the literature, as the H-alpha equivalent width, which is the area below the curve, below the emission line of the H-alpha, increases, which is saying that exactly inflation is increasing with H-alpha. And with a few statistical tests, it actually shows that it's real, it's not just by eye. This one kind of looks like it's something by eye, but when doing the test, there is no correlation there, and also not for the lower mass bands. So as I mentioned before, right now we don't have a way of testing, or with this method, we don't have a way of testing if there is no correlation of H-alpha as a function, the difference of radius, the radius inflation as a function of H-alpha for the higher mass stars, for the lower mass stars, if there is none, or it's just that we cannot measure it because it's getting too close to the uncertainty of our method. Just right now, the only thing that we can say for the lower masses is that they do look inflated, the active ones. Yes, I'm done. Thank you very much.
Okay. So thank you. Thank you very much for this nice talk. Are there questions over there?
Hello. Very good to talk. Do you consider include a stellar rotation in your study?
Yes, so we can study this same thing as a function of rotation. I did consider it, did not include it, is in the to-do list.
Very nice talk, Rocio. Thank you. I'm just curious about whether you've thought about doing some high resolution H-alpha spectroscopy for some of the maybe the brighter stars in the sample, if that's even possible. Because as you know, measuring the boundary between active and inactive gets very hard when the star is a slow rotator, an old star, and the emission gets very low. And so, refining really where that boundary is might be something worth considering.
Yeah, no, that's a very good point. So right now this study is statistical, right? We have a radius measurement that has a 4% uncertainty. So the advantage of this work is that we can apply to large samples and see a general trend. If we want to study a star in more detail, definitely using a higher resolution of H-alpha would help. What I always worried about H-alpha is the variability. So getting one spectra from an M-dwarf from one H-alpha, we might even don't see an H-alpha because it's super variable. So, but to do a study with high resolution spectra, I think we need to take several if we want to study one study in detail. One star in detail, at least to make sure to have at least an average of the H-alpha value that star has. Yeah.
Nice talk, Rocio. Maybe I missed this, but could you elaborate a bit on how stellar activity or why inflates a radius? What's like the physics happening there?
Okay, yeah, we could stay here for a long time. But yes, there are different ways that at least we think that is happening. The main two explanations is either there's a lot of magnetic field on the star, which inhibits convection, and that makes the stuff puffier. And then the other one is this spot coverage on the star that would also generate the same effect, like it would inhibit convection and it would make the star get puffier, so it gets bigger at a constant volumetric luminosity, so that makes the effective temperature smaller and the radius larger. That is like the general picture.
Hi, thank you for your presentation. I was wondering if you include some corrections in the parallax or something like the bias or Taylor corrections.
Added correlation on the corrections on the parallax. Well, I do trust a lot of the Gaia parallaxes. I'm of the opinion that they have great data. Also, these stars are very nearby. So what I did do to the parallax is make sure that they have good signal to noise. So I did make a cut on signal to, I think it was like 100 of parallax over error, making sure that the signal to noise was higher than that to make sure that the distance was actually accurate.
Okay, so thank you very much. Let's thank Rocio and all the speakers of the session.